Two.
Hello everyone. Today our team is going to present our chemistry findings on sodium-ion batteries, which is an upcoming alternative to lithium-ion battery. This presentation was made under the supervision of our mentor, Miss Ella Davidi, and was made by three interns. Firstly,
I'm Suli Sarah Janice. I'm 17 years old and I'm a rising senior. So I come from Burkina Faso, but I live in Côte d'Ivoire. And some of my hobbies are sciences, sewing, and environmental activities.
I'm Anushka. I'm a 17-year-old living in Assam, India, and I'm currently a high school senior. Some of my hobbies include nature journaling, sketching, and graphic designing posters.
and finally, hi, I'm Sad. I'm 16 years old. I live in Côte d'Ivoire. I'm a rising senior, just like them. My hobbies include painting, biotechnology, music, and robotics. And here's a self-portrait I did. So let's not now dive deeper into the purpose of our presentation. So, in our modern world, batteries have become an essential part of our everyday lives, powering various devices from phones and remote controls to electric cars. These devices all rely on this invisible energy source, the battery, that works tirelessly behind the scenes to keep our technology functioning. But specifically, what's a battery and how does it work? A battery consists of four main components working together in synergy to produce energy. And these components are two electrodes, one being negative called the anode and the other positive named the cathode, which are both respectively represented by the structure A and B on the scheme. A conductive gel or liquid where the ions travel, called the electrolyte, which is structure C, and finally structure D, the separator, which is a selective membrane between the anode and the cathode. The functioning of a battery relies on two major processes, charge and discharge. During the charging process, electrons are pushed into the anode while positive ions travel from the cathode to the anode, the movement of which is represented by the top arrow. And when discharging, on the other hand, the process reverses with electrons being released from the anode to the from the anode to the cathode and traveling, oh gosh, which is represented by the bottom arrow.
So there are different types of batteries, and each type has its own characteristics, uses, and performances. Among those types of batteries, we have lead acid batteries that you can see in the yellow circle, and these are one of the oldest rechargeable types of batteries, and you can find them in cars, backup power systems. For the second type, we have nickel-based batteries, and they are used in older electronics. You can find them in the green circle. For the third type, we have lithium-ion batteries, and they are the most widely used today. We find them in phones, laptops, and electric vehicles. For the fourth type, we have sodium-ion batteries that you can see in the white square, and they are still being developed right now, but are considered a promising alternative for the future to lithium-ion batteries. So now let's look at the two graphs below. One on the left side, the graph one shows a performance comparison, and this graph shows how different batteries performs in terms of two metrics. The first being the energy density, which describes how much energy they can store per kilogram, and the second being the power density, which describe how much power they can deliver at once. So as we move to the right, the batteries are lighter and store more energy. And as we go up, they become more powerful. For example, lithium ion batteries, which are in the top, are high in both energy and power density, which makes them ideal for portable and high performance devices. In contrast, the lead acid batteries are heavier and less efficient, but still useful for specific applications. And you can also see lithium metal batteries, which are in the top, sorry, and they perform very well, but they are considered unsafe as labeled in the graph. On the right side, we have a graph that shows the market share in 2024 for the rechargeable batteries. As you can see, lithium ion batteries clearly dominates, making up 65.8% of the rechargeable battery market, and their demand is also growing fast at an estimated rate of 12% per year. And this is basically explained by what we said on the graph one.
While lithium-ion batteries remain the dominant technology in many applications, there's growing interest and development in alternative battery technologies spurred by several factors. The main reasons for opting out of lithium batteries are that firstly, they are flammable and risky to use. Secondly, they have a very detrimental impact on the environment, with poisonous gases leaking out of the mining sites. And thirdly, the most important reason for finding an alternative for lithium battery is the limited availability of its resources. The availability of its resources is very limited. As we can see, graph A and B show the increase in the consumption of lithium-ion batteries over a span of 20 years. And in the next 100 years, studies have shown that the consumption of lithium will be so high that there won't be any lithium left for production of batteries. Since LIBs are posing such issues, research has come up with a better alternative of sodium-ion batteries. So why is sodium-ion battery better than LIBs? Firstly, sodium-ion batteries are cheaper, earth-abundant, and environmentally friendly. Sodium is 1,000 times more abundant than lithium, and it's available in seawater and common salts. And lastly, sodium is way safer compared to lithium-ion batteries. Sodium-ion batteries also have some limitations, like they have a lower energy density than LIBs, which is up to 200 watt-hour per kg for SIBs compared to up to 300 watt-hour per kg for LIBs. And they also have slower diffusion kinetics due to the larger radius of sodium ions. And lastly, the larger size of the sodium ion makes it harder to insert into tightly packed electrode materials, reducing diffusion speed and structural stability. So over here, we can see the charging and discharging process of sodium ions in a sodium ion battery on the left. And the graph on the right shows charging and discharging of sodium ion batteries. And this is how we can estimate the capacity for a battery. The red and the blue lines show the charging process from 2.5 volts to approximately 4 volts, and the green line sloping downwards is showing the discharging process.
So, among the key challenges that sodium ion batteries will need to overcome for large scale deployments is their operation under extreme thermal conditions. Adapting sodium ion batteries to extreme climates proves crucial for their widespread adoption. Let's consider, for example, their use in particularly hostile environments such as mountainous regions with freezing temperatures or remote areas, whether polar or desert. In this context, the data show that these conditions significantly degrade the performance of the battery. This is why, to become a truly competitive and sustainable alternative, sodium ion batteries must imperatively be designed to, firstly, preserve their energy capacity, secondly, guarantee optimal stability, and thirdly, ensure absolute safety, even under the most extreme operating conditions. Now, let's dive deeper into why temperature is such a critical factor for batteries. It all comes down to what's happening at the microscopic level inside the battery cells. So, when the battery gets too hot, two main problems occur. The first one being side reactions, and the second one being thermal degradations. And all those effects affects the battery, the electrodes in the battery. Secondly, when the battery gets too hot, um, two main issues occur. The first one is the electrolyte freezing. So basically, the liquid electrolyte, which is normally like water, start turning into more like slush, and below a certain temperature, it can fully freeze. Um, for the second effect, which is slow ion diffusion, uh, when the battery becomes too cold, even before the electrolytes freeze, the cold makes it more viscous, a bit like honey-like texture. And this sluggish movements means that our battery can't deliver power effectively. And most dangerously, if we try to charging to try if we try charging a really cold battery, instead of the ions moving smoothly and embedding in the anodes, they plate as metal, and this will form dendrites that can pierce the separator and cause short circuits. So we decided that we are going to focus more on how to fix the low temperature issue for sodium-ion batteries.
So this slide talks about the cycling stability of the sodium-ion battery. The x-axis shows the cycle number, which is how many charge and discharge cycles the battery went through. The left y-axis talks about the specific capacity, which is the amount of charge stored per gram of active material. And the right y-axis shows the Coulombic efficiency, which measures how much charge put in during charging can be recovered during the discharge process. So if the Coulombic efficiency is 100%, that means that all charge is usable. So over here, black dots are representing charge capacity, red dots are showing discharge capacity, and green dots are showing the Coulombic efficiency. In the first graph, at 100 milliampere per gram and at room temperature, the sodium ion cell maintains high Coulombic efficiency, but shows a steady decline in capacity from 85 to 40 milliampere hour per gram over a course of 100 cycles, which is indicating efficiency is high, but long-term capacity retention needs to be improved. And the second graph on the right is showing the cycling performance of a sodium-ion battery at a very low temperature of minus 40 degrees Celsius. So some key observations for this graph is that the battery has high specific capacity maintained, and it also has cycling stability, which is capacity values are nearly flat across cycles, showing good stability over time. And lastly, the battery shows high Coulombic efficiency of about 95 to 99%, indicating very little loss of charge per cycle.
So, like Jani said, we're going to focus on how to solve the temperature issues of sodium-ion batteries under really cold conditions. So we decided to focus on two main solutions, which are electrode architecture and uh, electrolyte design. So here's how the electrode design first can address cold temperatures. First, thin electrodes are essential. When electrodes are made thinner, typically in the range of micrometers rather than millimeters, the distance ion must travel is significantly reduced. And this shorter path length directly counteracts the slower ion movement caused by cold temperatures. Second, high surface area structures are crucial. By creating electrodes with intricate surface textures and patterns, the actual surface area becomes much larger than the geometric area. For example, what appears as a 1 square centimeter flat surface could actually have 100 square centimeters of real surface area due to its microscopic texture. And this dramatically increases the number of sites where electrochemical reactions can occur, maintaining high reaction rate even when cold slows down ion movement. And third and lastly, porous materials play a vital role. The network of interconnected pores throughout the material creates pathways ranging from nanometers to micrometers in size. And these pores allow electrolyte to penetrate deep into the electrode structure, ensuring ions can access reaction sites throughout the entire material volume, not just the surface. And as an example of solution, we thought of 3D printed carbon aerogel because it has this porous structure that can easily fit the three elements that I was discussing. Let's now move to electrolyte design. So, firstly, low freezing point solvents are essential because these specialized solvents maintain their liquid state and ionic conductivity at temperatures well below 0 degrees Celsius. And this prevents the electrolyte system from solidifying or losing functionality in cold conditions, like Janice was discussing about. And secondly, solvent mixtures and co-solvents are a possible solution because by combining multiple solvents with different properties, the electrolyte can achieve an optimal balance between viscosity and freezing resistance. And this precise formulation can ensure ions can move efficiently even as temperature drops. Thirdly, salt concentration requires careful optimization because the exact concentration of salt determines both ion availability and solution stability. For example, too much salt can risk crystallization in cold conditions, while too little reduces conductivity. And the optimal concentration maintains high ionic conductivity while preventing unwanted crystallization at low temperature. Fourth and lastly, property enhancing additives could be crucial because these careful selected compounds can improve the electrolyte stability and maintain efficient charge transfer between electrodes. And they specifically target the challenges of cold temperature operations, such as increased viscosity and reduced ion mobility. And as a solution proposal, we thought of Diaglyme because it excels as a low temperature electrolyte for sodium ion batteries. And it has flexible ether chains highlighted by the red part and metal end group, which are the two CH3 at the extremities. And they create a molecular disorder, that resists freezing, while simultaneously the strategical position oxygen form a relay system for sodium ion transport.
So finally, after reading a lot of research papers and acknowledging what Sad said about what we should consider, we come up with a promising solution to the cold temperature issue for sodium ion batteries. So the combination of our battery to solve this issue will be firstly for the cathode manganese dioxide on 3D printed graphene aerogel, and he basically explained why. So he mentioned the structure which provides excellent electrical conductivity and fast ion diffusion. He also mentioned its porous network, which helps ion transport at low temperature, and the high surface area, which maximize contact with the electrolytes, and the thin electrode design, which shortens diffusion path. Secondly, we choose as anode material sodium metal, and this is just our sodium source and this completes the cell pairing with the cathodes. Thirdly, for the electrolytes, we have sodium perchlorate in Diaglyme, and this enables stable cycling, and also it is compatible with manganese dioxide, which is our cathodes. And the fact that it is 1 mole for its concentration improve the ion availability, and we can include additives if needed for a very cold environment. So to sum up, the sodium ion batteries offer a promising alternative, being more abundant and cheaper and environmentally friendly than lithium. Sodium ion batteries also can operate under colder temperature if we include all the improvements that we mentioned, and this shows potential for diverse climate conditions. So, thank you very much for listening to our presentation. We had a good time making it.
Have a good day.
Have a good day.